Here is a quick introduction to AS Physics Unit 1, Matter and Radiation for the Key Stage 5 AS Physics AQA Spec 2450. It's one of 6 units, or sub-units in the first half of the AS course. It will cover particles, quarks, quantum phenomenon, electric current, direct current circuits and alternating current. Now, it builds upon GCSE, so we're thinking of idea of protons, neutrality or charge, and finally the idea of orbiting of electrons around the atom. So it's pretty much basic. So we need to know about the periodic table, and we've got on this side alkali metals. We then go into the transition metals as we go across, and then we have semi-metals and non-metals. So we need to know a little bit more about the numbers. So what have we got? Well, we've got the atomic number, number 5, or often called the proton number. We have over this side, we have the relative atomic mass. This takes into account isotopes. If we look down at the bottom here, boron 11 occurs naturally at 80.1%, where boron 10 is 19.9%. So when we work out the average relative atomic mass, we come to a figure of 10.8. We need to be aware of this at A level. Okay, if we go on a bit. Specific charge. Well, let's think about the amount of charge per kilogram of matter. So specific charge is measured in coulombs per kilogram, and we just simply take the charge of the particles as a group, every one of them together, so all of the positives maybe in a nucleus, and we divide it by their mass. Now, a lot of students get this wrong, and it's really simple. You've just got to do charge divided by mass and make sure that you use the correct numbers. So if it's an electron, the charge has got to be 1.6 and it's to the minus 19. Protons, 1.67 times 10 to the minus 27. Make sure you know how to use your calculator. We need to be clear as well, are we dealing with a nucleus or an ion or a particle? Now then, a typical exam question would look like this. A stable atom contains 28 nucleons. It's a low challenge thing. You need to write down the number of protons, neutrons, electrons. So 14, 14 and 14. Moving down to a specific charge question, calculate the ratio of charge over mass in coulombs per kilogram for a uranium nucleus. So it's 92 times the charge divided by the mass, or the nucleons, multiplied by the mass of each nucleon, which gets you 37.3 times 10 to the 6 coulombs per kilogram. Very simple, really. Let's have a look at what we've got later on. There's another example there where you're looking for a tritium nucleus. So again, we've got charge and then 3 times an atomic mass unit, or a third of E over mass of the proton, which gives you another number, 3.19 times 10 to the 7. Well, very familiar. You'll get used to seeing 10 to the 7 for this type of calculation. We need to be able to explain what happens for alpha, beta and gamma radiation in terms of their tracks and also in terms of Z and N. So we've got to think about how alpha decay loses 2 protons, 2 neutrons. We need to look at alpha particle decay in this type of way, where you've got a parent atom and then a daughter atom, and a helium nucleus breaks off and 2 electrons are lost. We need to think about beta decay in more detail. In this one, we're looking at the idea of the conversion of a neutron to a proton in beta minus decay, and so we go from Z and N to Z plus 1 and N minus 1, which seems a bit strange, but when we have that conversion in the nucleus and we drop to a lower energy level, the beta minus particle is going to spin off, and we're also going to get an anti-neutrino of an electron flavour, beta particle decay. Carbon dating, we should be aware of the whole process and the idea of neutrons being captured. Then we have a different decay, and finally we go back for a beta decay, so the nitrogen returns to its original form. We should be aware that carbon has lots of different isotopes. Plotted on a ZN graph, you can see that's not changing, is it? It's the same, but the mass actually goes up. Also, to think about the idea that in terms of stability, On one side, where you have carbon of 8, 9, 10 and 11, we have beta plus decay. So they're trying to get towards stable, whereas beta minor decay is going the other way towards stable. Gamma decay, Z and M won't change, but we're just getting a lower energy state. Now, the neutrino, we do need to know a little bit about the neutrino, and it's just the idea that there is a fixed amount of energy that's given out by beta particle decay, some of which is given to the beta particle, and some of it is given to the neutrino. We can display this with quite a nice diagram here, where whatever the energy is of the beta particle, you've got the other energy of the antineutrino, and they vary. This line can move up and down, but overall it's normally a constant one for the entire process. So whatever the amount is here, 0.54 MeVs, and we'll come to MeVs later, it's going to be shared between the two. And where does it come from? Strong force. If we start thinking about forces, we've got to start thinking about the quarks inside the atoms. You need to be able to understand these interaction graphs and see how this one is a combination of two. One is the repulsive, or it could be attractive force, Coulomb repulsion. The other is the strong force between quarks. And when you add the two up, then you have an electric force dominating at larger separations and a strong nuclear force at smaller. Now then, we'll leave it there because we've done quite a lot, but that should introduce you to atomic physics for AS.